So let's say we have the following function. F of x, y is equal to tangent of x plus 2y. And we are given that x is a function of both s and t. It's equal to s cubed times t. And y is equal to s times the natural log of t. And we want to find all the partials of f with respect to s and t. So we want to find both del f del s and del f del t. Notice I am writing partials because if we were to write f as a function of both s and t, it would be a function of s and t, right? It'd be a function of one variable, meaning when you take its derivative with respect to any variable, it's going to be a partial derivative. So let's draw our little map. F is a function of, at the first level, x and y. We have f of xy is tangent of x plus 2y. And then at the next level, both x and y are functions of both s and t. We got s and t down here, and we need both a path from x to s and from x to t, and a path from y to s, and a path from y to t. So that we have all the ways of getting from f to s and all the ways of getting from f to t. So let's just write out the expression for del f del s. When you're finding a partial derivative, really you should be thinking every way I can get from the function to the variable. So how many ways can I get from f to s? Well, I can either go through x or through y. So going through x, we're going to have del f del x times del x del s. Going through y, oops, we're going to have del f del y times del y del s. Those are all the ways of getting there. And then we're going to find the things. So the partial derivative of f with respect to x, well, the derivative tangent of anything is secant squared of whatever you've got. So secant squared of x plus 2y multiplied by the derivative of the inside. So del x, times, the derivative of the inside, which is del, did I finish that part? Oh, I'm sorry. I'm getting a little ahead of myself. Sorry. So this the derivative of tangential stuff is secant squared of the stuff times the derivative of the inside, which is 1. Sorry. And then we have to multiply by del x del s. The del x del s is going to be 3s squared times t. Label things here. So there's our del f del x. There's our del x del s. Sorry, I got a little carried away with the chain rule there and started thinking of the derivative of the inside as the derivative of this part here, but that's over here. Plus, now we're going to do del f del y. The derivative tangent of some stuff is still secant squared of the stuff. But now when we use the normal chain rule, the derivative of the inside part with respect to y is going to be 2. And then we have to multiply by del y del s. The derivative of this piece over here with respect to s is going to be 1 times the natural log of t. So there is your del f del y. There is your del y del s. Questions so far? If it were up to me, I would leave it like this, but some people would have you then input what x and y were equal to in terms of s and t, if you wanted to write the derivative as a function of s and t. It is, yeah, it is. So one more time. Is it ordinary? I mean, what do you mean by ordinary? I took the so I shouldn't have looked over here. So I should have just said, if I'm just looking at this with respect to x, the derivative tangent of some stuff is secant squared of that stuff times the derivative of that stuff. So secant squared of my stuff times the derivative of that stuff, which is 1 if I'm doing it with respect to x, which is 2 if I'm doing it with respect to y. And then we're multiplying by del x del s here. The derivative of s cubed times a constant is 3s squared times that constant. And del y del s here. The derivative of s times the constant is 1 times the constant. Cool. Why don't you all try finding del f del t? Right, we'll write it out. Del f del t is going to be del f del x times del x del t plus del f del y times del y del t. So go ahead and find that. Part of it is already there for you. I'll give you a minute or so. The nice thing about finding this other partial derivative is that the del f del x is the same as it was before. So when we find del f del x, it's still going to be secant squared of x plus 2y times 1. But the del x del t part is going to change, right? Before it was del x del s, which is 3s squared times t. Now del x del t is going to be this constant s cubed times the derivative of t, which is 1. So you're just going to get an s cubed there. Plus, same story over here. Del f del y is the same as it was before. It's secant squared of x plus 2y times 2. But now del y del t, well, the derivative of derivative of a constant times natural log of t is that constant times 1 over t. Or you could write s over t. Those would be your partial derivatives. Any comments or concerns? Or move on to something similar but slightly different? Yeah.
For this type of question, do we really just get asked what is
Yeah, like they might even write out the words like find the partial derivative of your function with respect to x or t or s, and yeah. So let's look at this implicit differentiation step, which is really the same thing. It's just kind of a twist on it. So let's see. Yeah, let's start with that. So way back in 17a, we learned about implicit differentiation, and we were given something like, for example, x cubed plus y squared plus x times e to the y equal to 7, and we were asked to find dy dx, the derivative of y with respect to x. And when someone says find dy dx, the implication is that y is a function of x. Right? They're asking you to find the derivative of y with respect to x, meaning how y is changing as x is changing. That means we are assuming that y depends on x. So when we differentiate this, we're going to make the assumption that y is some function of x. So here's the old way of doing it. Take the derivative of everything with respect to x. So the derivative of x cubed. Now, we need to be careful here, right? It's not like we're taking the partial with respect to x. We're taking the derivative of everything with respect to x, and we're assuming that y is a function of x. So the derivative of x cubed is going to be 3x squared. The derivative of a function of x squared is going to be 2 times that function of x to the first times the derivative of that function of x. Chain rule. Or as I would say, if you've got some stuff squared, the derivative of some stuff squared is 2 times your stuff times the derivative of your stuff. Plus, for x times e to the y, we're going to have to use the product rule. The derivative of x is 1 times e to the y, plus, leave the x alone, the derivative of e to the y, well, the derivative of e to the stuff is e to the stuff times, not everybody all at once, not 1, the derivative of the stuff. So the thing here is that the derivative of x is 1. The derivative of y is the derivative of y, which is y prime. Because we don't know what y is. Y could be like tangent of x cubed plus 1, but we just know that y is some function of x. So the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And then the derivative of 7 is 0. And then we would do a bunch of algebra where we would solve for y prime. So I noticed that there is a y prime in this term and a y prime in that term. So I would leave those on the same side or bring them to the other side. I'd probably write this as 2y times y prime plus x e to the y times y prime equal to, I'd bring this over to the left. So I'd have a negative 3x squared minus e to the y. I'd factor out a y prime. I'm left with 2y plus x times e to the y equal to the same stuff. And then finally, I divide both sides by 2y plus x e to the y to get negative 3x squared minus e to the y divided by 2y plus x e to the y. And that'd be a perfectly fine way of doing it. However, we don't have to do it that way. Oh, and actually, I'm gonna make one more simplification just so we can see the thing I've lost. Actually, I'm gonna write this as negative parentheses 3x squared plus e to the y over 2y plus x e to the y. Because now we're going to do it the new way, and I figured this fit. So the idea with the new way is first to bring everything to one side. So we're going to rewrite this as, and leave yourself some space on the left here, x cubed plus y squared plus x e to the y minus 7 equal to 0. And we're going to call this function that's equal to 0, we're going to call that capital F of xy. So now we're thinking of capital F as just the normal kind of partial derivative thing where f is a function of x and f is a function of y. And now we're going to differentiate both sides with respect to x again. So we take the partial derivative with respect to x. Well, the partial with respect to x of x cubed is going to be 3x squared. I have to make sure I'm thinking of this the right way. Sorry. My brain is, oh yeah, okay, sorry. Yeah. Sorry. Yeah, okay. Yeah, let me back up just one second. This is something that I've over the years, I'm like, how's this work again? Okay, yeah. So what we're gonna do is we're gonna take the derivative of f. So we're gonna see that f depends on x and y, but really we're thinking of y as a function of x, so y also depends on x. So x and y both actually depend on x. So watch this. We're gonna take the partial in the usual way. My df dx is going to equal the partial with respect to y times the derivative of y with respect to x plus the partial of f with respect to x times the derivative of x with respect to x. What's the derivative of x with respect to x? Right. So that's going to be a 1. And on the other side, right, so I'm pretending like this is my whole equation on the left. There's my f of xy. On the right-hand side, the derivative of 0 is going to be 0. this leads us to the following equation. If we want to solve for dy dx, well, fy times dy dx is going to equal negative fx. And if we divide both sides by the partial of f with respect to y, we end up getting that dy dx is equal to the negative of the partial of f with respect to x divided by the partial of f with respect to y. Let's take a look. If you look at this thing we've written here, the partial of f with respect to x is exactly 3x squared. Derivative of y squared is 0. The derivative of x e to the y is 1 times e to the y. Divided by the partial of f with respect to y, derivative of x cubed is 0. The y squared is 2y. Derivative of x e to the y is x e to the y. Oh, sorry. Zoom out a little bit. Sorry. Okay. Let me do this. That'd be smart. There we go. It's a little bit better. So, is it better? Maybe. So we can see that doing it this old way, where we just took the derivative of everything with respect to x and then solve for y prime, or doing it this other way, where we just say that the derivative of y with respect to x is just the negative partial of f with respect to x over the partial of f with respect to y, both yielded the same result. So that's the idea. There's this kind of shortcut for taking the partial, the derivative implicitly. Let's look at another example. I'll try and leave this one up still. Yeah, question. If you have more variables, you can. Let's take a look. So it's tricky. So it is tricky because you have to kind of remind yourself of something. But let's say we had an example with more variables. Let's say we've got the following. Sure. Let's say we've got x squared plus y cubed plus z to the fourth is equal to 3xy z. And we want to find del z del x. And the reason I'm writing del z del x instead of del dz dx is because if you solve this thing for z, you have to have z as a function of x and y. So that's why I'm writing del instead of d. So if I want to find del z del x, let's do it the short way first. So I'm going to say that this is equal to, well, first of all, I have to rewrite this. So let's rewrite this as x squared plus y cubed plus z to the fourth minus 3xyz equal to 0. And this thing that's on the left-hand side, that is our capital F of x, y, z. The short way of doing this, it's not too hard once you've done it a few times. You just say, okay, it's going to be negative, and you just flip these over. So if you're finding del z del x, it's going to be the negative of fx over fz. The partial of f with respect to x over the partial of f with respect to z. Cool, let's do it. So when I take the partial of this whole thing with respect to x, I'm treating everything else, y and z, as constants. Derivative of x squared is 2x. Derivative of y cubed is 0. Derivative of z to the fourth is 0. Derivative of negative 3x times y times z is negative 3 times y times z. Divided by fz. So the partial of all this with respect to z is going to be 0 plus 0 plus 4z cubed and minus 3 times x times y times 1. There's our short way of doing it. Let's talk about how we would do it the long way. Again, not that you need to, but it's kind of nice to see. And I feel like I don't know if it was on the quiz. I think it was on the quiz. Like there were some questions like this where you had like to bring everything over to one side, and then you had to take the derivative of both sides, and it was very kind of like just unsimplified looking. Like you just took the derivative of both sides. It was a little bit odd, but fine, just different. So here's how you could do this the long way. So again, we are making the assumption if we are finding del z del x we are assuming that z is a function of x. Let's call it, yeah, sure, we'll left with x. It might also depend on y, but if you're differentiating with respect to x, so I think words would be better here. We are assuming z is a function of x. Yeah. I missed it completely. Thank you so much. I was going to get to the end and it was going to be off by a negative. Oh my gosh. I would just put the negative out in front. If you want, you can write it as negative parentheses 2x minus 3yz over 4z cubed minus 3xy. Good call. Thank you. So for example, when we take the derivative with respect to x of like z to the fourth, we're going to get 4z cubed times dz dx because we have to multiply by we have to use the chain rule. So let's differentiate. We're assuming x is the variable. We're holding y constant because if we're differentiating with respect to x, we're saying x is changing. We're holding everything that's not x or depending on x constant. So the derivative of x squared is going to be 2x. And I'm just going to use this version here because I can. The derivative of y cubed is going to be 0. The derivative of z to the fourth, since we are assuming z depends on x, is going to be 4z cubed times del z del x. Equal to, I have to use the product rule on the right-hand side now. I have 3x, a function of x, times yz, a function of x because z depends on x, because we have said we're finding del z del x. So the derivative of 3x is 3 times the other piece. Let's leave the 3x alone. The derivative of yz is, well, y is just a constant, and the derivative of z is the derivative of z. I always feel silly to say that the derivative of z is the derivative of z, but we really do mean that, right? The derivative of z isn't 1. The derivative of z is z prime or del z del x or however you want to write it. Because in my mind, I'm kind of like thinking z could equal x to the fifth plus cosine of x, for example. And so then if I took the derivative of that thing to the fourth, I would get 4 times that thing cubed times the derivative of that thing because of the chain rule. Same deal over here. If you use the product rule, the derivative of 3x times yz, I'm getting 3 times yz plus 3x times the derivative of yz is y times the derivative of z, whatever I'm pretending that z is equal to. And now we do all the algebra. So I'm going to try and solve for del z del x. I've got that term there and that term there that both have a del z del x. Let's bring all of those to the left. So I'm going to have 4z cubed times del z del x minus 3xy times del z del x equal to, subtracting 2x over there, I'm going to get negative 2x plus 3yz. Factoring out the del z del x and dividing by what's left over, I'm going to get del z del x equal to negative 2x plus 3yz divided by, I'm going to have, I factored out the del z del x, I'm left with the 4z cubed minus 3xy. Same. Certainly computationally easier to do the first thing. Not just computationally, I think also like inside your head, right? Like it's much more mental work to be like, oh yeah, z is a function of x. So when I take the derivative of z to the fourth, I get 4z cubed times z prime. Whereas up here, you're just kind of throwing a formula out. You're saying, okay, I want to find del z del x, it's negative fx over fc. And in a similar way, we could then ask what's going to be del z del y. You could actually ask this for any combination, right? You could say what's del x del y del x, del z del x del, right? You could do it any way you want. So somebody said, now what's, instead of doing del z del x, what if somebody said, well, now I want to pretend like y is a function of z. What's del y del z? Oh, sorry, you can't quite, sorry, I'm It's always hard to see where I am here. Apologies. So now del y del z is just going to equal, same idea. The thing that's on top goes on the bottom. The thing that's on the bottom goes on the top. And then you slap a minus sign in front of it. I'm still using the same capital F. So now capital FZ is still going to be, don't forget the negative sign. I don't know who would forget the negative sign. We're going to get a negative 4z cubed and a minus 3xy. That's your FZ, same as it was on the denominator of the previous problem. And then Fy, the partial with respect to y, is going to be 3y squared minus 3xz. And while you could do this the long way, I don't think we want to. I think the way your teacher has kind of been more, at least what I saw from the quiz problems, the way your professor has been more imagining it is we're thinking of having f of x, y, z equal to 0. And then when you take the derivative of both sides, well, again, we're imagining f as a function of x, y, and z. And then all of these things depend on whatever variable we're talking about, kind of. So when I take the derivative here, if I differentiate both sides, the derivative of f with respect to, let's say we're doing with respect to x, we're going to get del f del x times dx plus del f del y times dy dx plus del f del z times dz dx equal to 0. And then if we're saying that we want to find, for example, if we want to find like dz dy, well, that means z depends on y and x doesn't. So sorry. So you shouldn't ask that question if you've done this. I'd have to do with respect to y on the bottom. If I asked instead the smarter question, sorry, brain, del z del x. It's really hard sometimes when your hand doesn't want to write the thing your mouth is saying, or when your hand is already like, I'm going to write this, and then your mouth is like, I'm going to say this. Or if I del z del x, then what we're saying is z depends on x is changing, and y doesn't really depend on x. So we're essentially saying for this situation, del y del x is going to be 0. And we know that dx is going to be 1. So we're left with, not surprisingly, del f del x plus del f del z times the thing we're trying to find, del z del x equal to 0. And that's exactly how we're getting to del z del x equal to negative the partial of f with respect to x divided by the partial of f with respect to z. So that might have been more the path that your instructor was taking to kind of show you how we're getting there. Still the same word. Yeah, Maddie.
Can you describe how the del y del x is 0?
Right. So when I say find del z del x, what we're assuming here is we are assuming x is changing, z depends on x, because we're really asking how is z changing as x is changing.
So no matter what, I can always say that if it's asking for 2 variables, and
The odd man out, like if there's a third variable, that one is acting like a constant.
okay, so we'll just
Right. Because basically if you're asking how is z changing as x is changing, I don't want the other variable to be changing. So if I'm saying how is z changing as x is changing, well, I'm going to hold y constant because I'm only trying to figure out what z is doing as x is doing whatever. So y gets to hold constant, and then when you differentiate, the derivative of that constant thing gets to be 0.
okay.
Yeah, it's very kind of nuanced, but I think that your question really kind of got at it there. So all this really is here It's just how we are using the chain rule and partial derivatives to make it easier to do implicit differentiation. That's all this is. So if someone says, find, look at this thing and find dy dx implicitly, the assumption in this class is that you're going to use this kind of formula. You can still do it the old way, but it's much faster to do it this new way. So let me give you one more to try on, and then I think we'll move on to talking about other things like the gradient. Why don't you all try the following? Let me give you a new piece of paper here. Let's try the following. I have one right off the bat here. Let me just make something up. So let's say you've got, x to the fourth z cubed plus x cubed y to the fifth plus, why not? Y cubed z squared equal to cosine of x to the fourth. And I want you all to find the short way. I want you to find, what do I want you to find? Sure. Let's find del y del z. And I'll remind you, your first step should be rewriting your equation so that you've got everything on the left equal to 0. That should be your first step before you do anything else. Oh. All right, let's see what we've got here. So our first step, if we're trying to do this fast way, is to write everything equal to 0. So we just bring over we subtract cosine of x to the fourth from both sides. And then if we want to find del y del z, It's going to be the negative of the partial of f with respect to z divided by the partial of f with respect to y. So now we're going to get del y del z equal to negative. So looking at this here, the partial of f with respect to z, I'm going to get x to the fourth times 3z squared, or 3x to the fourth times z squared, plus 0, because the derivative of x cubed y to the fifth, there's no z's there. And then the derivative of y cubed z squared is going to be 2y cubed times z. And the derivative of cosine of x to the fourth is 0 as far as z is concerned. And the denominator, same deal. I'm taking the partial with respect to y. So for this first term here, the derivative of x to the fourth times z cubed is going to be 0. The derivative of x cubed times y to the fifth is going to be x cubed times 5y to the fourth. So 5x cubed y to the fourth. And the derivative of y cubed times z squared is going to be 3y squared times z squared. And the derivative of cosine of x to the fourth is going to be 0 again, because there's no y's in it. Could you simplify this? No, I don't think so. And should you simplify this? No, you should not. Unless if there's something like really obvious, you should almost never simplify these implicit derivatives here. Cool. So let's move forward. Unless there's questions. Questions.
Yeah, I have a quick question. But if that's fine, del y, del z, should I ever just dy, dz?
Well, so that could be a matter of opinion. It really kind of depends on what. So you could imagine that if we solved this equation for y would both depend on both x and z. So that's what's in my mind. That's why I'm writing del y del z instead of dx dy dz, because I'm imagining that y could maybe depend on both x and z.
And that's what I was trying to ask, but when we were going to change over to then you have it in
From back here.
Yeah, del x, del d, and I thought it should be df.
So no, and the reason it's not df ds is because if at the base level, like if I actually rewrote this, putting in what x and y were, I'd have that f of s and t is tangent of x, or sorry, is tangent of x, which is equal to s cubed times t, plus 2y, which is equal to 2 times s times natural log of t. And so we see that f is a function of more than one variable at the base level. That's why I'm writing del f del s, because it's a partial derivative. So usually, oh yeah, question. The problem we just did. Okay, cool. Other questions? All right. Yeah, go ahead, Jocelyn. Yes. Yeah. It's really kind of great. Right, whatever. So basically, when I look at this, I see, okay, I see del y on top, and I think of the y going down there. And I see del z on the bottom, I think of the z going up there. And then there's a negative sign in front. And that's it. And it's kind of weird, but it feels like kind of a formula that shouldn't maybe work all the time, but it totally does. Let's move on to talk about directional derivatives. So we have already talked about a couple directional derivatives. The derivative in the direction of x and the derivative in the direction of y. The partial derivatives we've been talking about are directional derivatives. We're asking, as you move forward in the x direction or forward in the y direction, how is the function typically thought of as a surface? How is that changing? So, but now we want to say, maybe I want to go in the direction that's like not x or y, but that way or behind me or something else. So we need a more general definition of a derivative. Before we can do that, we need a little bit of review just to make sure everyone's on the same page. So a couple quick things. First thing, dot product. So if you got two vectors, u and v, and some angle theta between them, one way of taking the dot product, which is not particularly usually easy to compute, is that the dot product u dot v, and do say dot, we don't say u times v. There really is, there's no like regular vector multiplication. It is the vector u dotted with the vector v is equal to the length of u times the length of v times the cosine of the angle between the two vectors. I will point out this, when you dot product two vectors together, your answer is a scalar or a number, right? You don't get a vector back. It's also called the scalar product because it gives you a scalar back. The nicer way of calculating a dot product is if you know the components of your vectors. So for example, if u is equal to the vector AB and v is equal to the vector CD, then calculating u dot v is just multiplying the corresponding components of the vectors together and adding up the results. So A times C plus B times D. That is how you take the dot product of two vectors in the easier way. So for example, if my vector u is, say, the vector 1, 4, and v is the vector 5, 2, I could draw them. Right? It's not hard to draw them. 1, 2, 3, 4, 5. So u looks like over 1 and up 4. V looks like over 5 and up 2. So maybe there's u in red, and here's v in black. I don't know what the angle is between them. I mean, I know it's less than 90 degrees. If I worked really, really hard, I could probably find it, but that's not the point. The point is that I can find u dot v by just calculating 1 times 5 plus 4 times 2, which is equal to 5 plus 8, which is 13. I will mention there's not really a good geometric interpretation of the meaning of the dot product. Like sometimes, like when you add vectors together, you just put one on the end of the other and it looks like a parallelogram. If you really want to get into it, the dot product is kind of like how much of each vector is in the other vector's direction multiplied together, but that doesn't really roll off the tongue. So luckily it's easy to calculate. So now I want to do something that's going to give you a little bit of motivation as to why the directional derivative actually works the way it works. Because you might have just, I don't know what you did in class, you might have just been given a formula, but I want to show you just a little bit more. And for this next part, I mean, you're always welcome to write down as much as you want. You probably don't need to write down as much of what we're about to do, but you certainly can. So let's look at this. Something that seems maybe not super related, but trust me, it is. We're going to look at the parametric equation of a line. So here's our line. We're going to call it L. And it goes to the point 1, 2, and the point 4, 7. And the problem is describing a line in 3 dimensions, you can't just use a point and a slope. You need a point and a direction. Because slope is, I mean, you can have lots of lines with the same slope that are pointing, that way, that way, that way, that way, that all go like over 1 and up 2. So we need a point and a direction. So what I'm going to say here is I'm going to let this point, I'm going to think of this as starting at t equal to 0, often thought of as time. And then 1 time unit later, maybe it's 1 second or 1 minute or whatever, t equal to 1. So what we're going to do is we're going to imagine a particle moving along the line from the point 1, 2 to the point 4, 7 at a constant speed. So in 1 second, it's going to go from here to there. Okay, let me ask everybody. If it's going to go from the point 1, 2 to 4, 7 in 1 second, where am I going to end up if I go another second at t equals 2? Well, from t equals 0 to t equals 1, how much did the x coordinate increase by? So it probably going to happen again since I'm moving at a constant speed. And how much did the y coordinate increase by? Right, so 7 plus 5 is 12. So I would expect that at t equal to 2, I'd end up over at the 0.7 comma 12. So the idea here is that we can think of the x coordinate as our starting x coordinate plus how much we're increasing every time we increase t by 1. That's going to be 3 times t. And we can think of our y coordinate as, well, we're starting at y equal to 2. And then every time we increase t by 1, we're increasing y by 5. And these are our parametric equations for this line. I will point out, just because you might see this, you could also write this as the vector x of t, y of t equal to 1, 2, your initial point, plus t times 3, 5. And I would point out, that 3, 5, that is your direction vector. That is telling you what direction the line is going in. Always over 3. I know I didn't draw it like that because it's weirdly oriented in space. Over 3, up 5, over 3, up 5, over 3, up 5. Again, I know picture not perfect. Okay. So hold on, promise. It's good. We're gonna get there. It's gonna be neat. So let's look at the following thing. Yeah, so I should do, yeah. So let's look at this surface. I think I've mentioned the surface before. F of x y equal to 9 minus x squared minus y squared. It's a downward opening paraboloid. Looks like this. I can draw some axes here if you like. There's my y-axis. X-axis. Z-axis. And we're going to look at the level curve when z equals 4. So z equals 4. Z equals 4? Yeah, z equals 4. I'm going to go up. 1, 2, 3, 4. My level curve is a circle. Specifically, we're going to look at the same point. I know it's been a while. We're going to look at the same point we looked at before, which is the point 1, 2, 4. So I'm going to 1 in the x direction, 2 in the y direction, and then 4 in the z direction should get me right about there. Yeah, so that's the point 1, 2, 4. And what I'm interested in now is I want to find the slope of the tangent line at that point to the surface, but in what direction, right? I could ask it in the x direction, and I think last time we did it was -2, or I could ask it in the y direction, and the slope was -4. So the slope of the tangent line depends on what direction you are pointing, which I know is not easy to see, and I wish I had something that shaped. I turn this over, it's going to pour all my water out. That'll be a bad idea. I don't have any cones. All right, so sure. So pretend this is your surface, right? If you are, sorry, and sorry for the people at home. So if you're like right here, well, if I go that way, the slope is like 0 because I'm kind of just living on this line that's at that level. But if I go that way instead, the slope is super duper negative. So even though you can be at a point, it's kind of like, I mean, really, if you were walking on a hill, right? Say you're on the side of a hill, well, you can keep going in a direction that's going to kind of just keep you level, but you can also like make a sharp left turn and go really steeply up. or a sharp right turn and go really steeply down, right? So at any point on your surface, there are lots of different directions that have different derivatives. Let's look at one in particular. Oh, where are my papers go? Sorry. So this is where things get a little bit dicey. So we want to find the following. The derivative of this surface at the point in question, 1, 2, 4, in the direction of the vector v equal to 4/5, 3/5. And sorry, I've written my vector in a different way than usual. Sometimes people write vectors in different ways. That's what we're going to do. And the way we're going to do it is by parameterizing the line in that direction. So let's draw another picture here, that you can see maybe. So I'm just going to draw the level curve. So I'm going to take that same circle. Can I draw a circle? Maybe. That's all right. So here's a height of z equal to 4. And here's my point where x is 1 and y is 2. So here's the point 1, 2, 4. And now what I'm saying is that point right there is the same as that point right there. I'm just drawing in 2 dimensions. And now from that point, I want to go in the direction of the vector 4/5, 3/5. Or as I'm really not going to draw it like that. I'm just going to think I'm going over 4 and up 3. 4/5 is 4/3 of 3/5. 4 is 4/3 of 3. I'm thinking going over 4, up 3. So kind of in that direction. So I'm going to draw that line. And here's what I know about this line, which I'm going to call L. That line can be parameterized by, well, if I think of this point here, 1, 2 is when time is equal to 0, then my x coordinate is going to be 1 plus something. My y coordinate is going to be 2 plus something. But if I'm going in the direction of the vector 4/5, 3/5, so I'm going, and of course I drew this and put this in the exact wrong spot. Sorry. I'm going over 4/5 and up 3/5. Well, every time I increase t by 1, I'm going to increase x by 4/5. So I'm going to get 4/5 times t. I'm going to increase y by 3/5. I promise you, this is going to end up somewhere really cool. It's going to take like a little, just hang with me for like another couple minutes and we're going to be like, oh, that's great. So, promise. All right, so I want to find the slope or the derivative of my function f of xy equal to 9 minus x squared minus y squared in the direction of the vector v. Well, look, f depends on x and y. What do x and y both depend on? Well, it sounds like a chain rule situation. F depends on x and y. And x and y both depend on t. So if I want to find the derivative of f with respect to t, df dt, it's going to equal del f del x times dx dt plus del f del y times dy dt. And before I get to actually calculating for this particular example, I want to point out that this is actually exactly what we're looking for. This is, let me write this a different way. This is the vector del f del x del f del y dotted with the vector dx dt dy dt. But look, if x is equal to 1 plus 4/5 t, what's dx dt equal to? What's the derivative of 1 plus 4/5 t? Yeah. So this is equal to the second vector, the first component is 4/5, and the second component is, oh, that's just my vector v, right? I said v was the vector 4/5, 3/5. So that's just v. And the partial of f with respect to x and the partial of f with respect to y is the gradient of f. So what we have is the gradient of f, and I should put an arrow over that, dotted with the vector. Oh, holy smokes! Of course, it's terrible. Sorry. The gradient of f dotted with the vector v, and that is the derivative of f in the direction that we were looking at. It's kind of cool. In this particular example, our gradient ends up being, well, the gradient of f is the partial with respect to x is going to equal negative 2x. Partial with respect to y is negative 2y. We do have to plug in the point. So at 1, 2, dotted with 4/5, 3/5. And then that actually ends up equaling, well, by plugging 1 for x and 2 for y, it's negative 2, negative 4, dotted with 4/5, 3/5. So that ends up equaling, sorry, and I'm squeezing this in over here, negative 2 times 4/5 plus negative 4 times 3/5, which ends up being negative 20 over 5, which is negative 4. Feels slightly wrong for some reason. Nope, that's all right. So what that means is, looking, sorry, I know you guys know. So what it means is back on this surface, if we move in the direction that is going 4/5 in the x direction and 3/5 in the y direction, sorry, that's the y direction, 4/5 in the x direction and 3/5 in the y direction. So kind of, this is where it's gonna be kind of terrible. If I'm moving out that way towards you, the tangent line in that direction has a slope of negative 4. Kind of cool. Actually, I think I'll be honest, I think it's really neat, to be perfectly frank. Directional derivatives are kind of like, oh wow, you can take the derivative of the surface in any direction you want. So to kind of summarize here, the derivative of a function of x and y in the direction of the unit vector u is going to be given by, sorry, at the point x naught, y naught is given by the gradient of f evaluated at x naught, y naught dotted with the unit vector u. And we write that as d u f, the derivative of f in the direction of u. Okay, questions about any of that before we do a couple examples? Yeah.
Before this derivative, before the rational derivative, we were just going along. The unit actually 1, 0, and then
Exactly. So if someone said find the partial derivative of the function with respect to x, you can really think of that as the directional derivative in the direction of the vector 1, 0. And it ends up being, right, which check that out, right? So for example, if I find the very just generally the derivative of f of xy in the direction 1, 0, which is a unit vector, right? It's a vector of length 1 in the x direction. Well, look what you get. It's going to equal the gradient of f dotted with the vector u. The gradient is the partial of f with respect to x, partial of f with respect to y, dotted with the unit vector, which is 1, 0. And that just ends up being the partial of f with respect to x times 1, plus the partial of y with respect, partial of f with respect to y times 0, which is just the partial of f with respect to x. So it totally makes sense that the partial derivative of f with respect to x is the directional derivative of f in the direction of x. Yeah, always, yeah. Is that better? What are you trying to see?
I'm trying to see if it's minus 8/5 minus.
It-
12/5.
Yes, it is. It's minus 8/5 minus 12/5. Cool. So 20 minutes. Awesome. Or almost 20 minutes. So let's look at some examples. And there's two things I want to make super clear because they come up often. So let's say new function. Let's say my function f of x, y is equal to x cubed minus 3y squared plus 8. And I want to find the slope of f at the point 2, 1 in the direction of the vector. Sure. Let's make it somewhat nice. -5, 12. You might notice the vector that we've been given is not a unit vector. It's way, way longer than a vector of length 1. So when that's the case, we have to normalize or unitize our vector when we do this. I'm still just going to go the usual way. So I might say that if we're given v equal to -5, 12, well then our unit vector is just going to be the vector v divided by the magnitude of v. So let's see, I'm going to get the vector -5, 12 divided by the magnitude, which is the square root of -5 squared plus 12 squared, which happens to be a nice integer number. 5 squared is 25, 12 squared is 144. You add them together, you get 169, and the square root of 169 is 13. So you're going to be getting 1/13 -5, 12. And I would honestly leave that 1/13 out in front. I don't think there's any value really to distributing it in and writing my vector as -5/13 and 12/13. So now let's do the calculation. Our DUF at 2, 1 going to be, well, the gradient. So my gradient is going to be 3x squared in the first coordinate and -6y in the second coordinate. I'm going to evaluate that gradient at 2, 1. And I'm going to dot that with the unit vector I just found. 1/13 -5, 12. Constant multiples can come out, you can put them anywhere in the process of the dot product. So I would probably rewrite this as 1/13 times the dot product of now plugging in 2 for x and 1 for y. 3 times 2 squared is 12. -6 times 1 is -6. So we got 1/13 times the dot product of the vector, 12, -6, and -5, 12. So let's see, calculating that, I'm going to get 1/13 times 12 times -5, or -5 times 12, plus -6 times 12. Which I could do, right? -5 times 12, -60, -6 times 12 is -72. Or I could just factor out the 12 first and write it as 12/13 times -5 minus 6, which is 12/13 times -11, which is 11 times 12 is 132, so -132/13. So slightly more steep than -10. Pretty steep. I mean, a steepness of 10, like you go over up 1, up 10, or 1 down 10. All right, here's the thing I actually want you to see. Well, okay, I want you to see all the things. But one thing I want to point out is, well, let's say I ask the same question, but I'm gonna change it up just a tiny bit. So, and this is where I've definitely seen some people on either, I think on both, actually on Piazza and Discord, are struggling with this one little thing. Like they think they're writing the right answer into web work, but they're off by this. So let's say I said, I want to find, same deal, find the slope of f of xy equal to x cubed minus 3x squared plus 8 at the point 2, 1 in the direction of, let's say I have, I don't know, let's make it 6, 8. This is where someone might be trying to kind of fool you. So the way that is written, am I finding the slope of this function in the direction of the vector 6, 8? Or is that not a vector? It's a point. So the vector that's actually giving us our direction, our vector, our direction vector, is actually the vector that takes us from the point of tangency to the point that we're going towards. The vector, I'm just going to draw it. It starts at the point 2, 1, and then ends at the point 6, 8. So our vector is, well, the x coordinate is 6 minus 2. The y coordinate is 8 minus 1. Technically, so when people say direction vector, they usually mean unit vector, but really this vector is also the direction vector. It's pointing in the correct direction. We just have to make sure that when we find the answer here, we normalize our answer. So let's find our gradient. Our gradient is the same as it was before. It's 3, oops, that's a 3y squared. Sorry, I wrote an x there. Should be x cubed minus 3y squared. Sorry about that. Our gradient in general is 3x squared and negative 6y. Our gradient at the point of tangency is just going to be 3 times 2 squared, negative 6 times 1. That's 12, negative 6. And then our directional derivative is going to equal the dot product of these two vectors. So my gradient dotted with my direction vector, but then I know I have to divide by the magnitude or length of my direction vector. I usually like to write this as 1 over the square root of 4 squared plus 7 squared. And again, I think it's really in your interest to write that outside. You don't need to put that inside the vector. So let's see. I'm going to get 12 times 4 plus negative 6 times 7 all over the square root of 16 plus 49, which is going to be 6 over the square root of 65. And that is the slope of the surface at that point in that direction. Let's continue with this example. For the same function here, so still for f of x, y equal to x cubed minus 3y squared plus 8 at the point 2 comma 1. In what direction does this function increase most rapidly? Or essentially, in what direction would you be walking up the hill in the steepest way possible? So we're trying to find the direction u so that d u f, the directional derivative of u in the direction of f, at the point 2, one, we write that at the end, which is equal to the gradient of f dotted with the direction u. We want to maximize this. It seems hard to think about. So like, if I was going to write this in like the easier way of computing it, where you're doing like the components of f times the components of u, and then you want to maximize that thing, that seems challenging. But it's not if we remember the other way of calculating the dot product of two things. So another way of calculating the dot product is the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So like if that's my gradient of f, that's my vector, my unit vector u, there's the angle between them. So if I want to make this expression as large as possible, well, first off, the gradient of f isn't going to change, right? That's just take the partial derivatives, plug in the point, and you get a vector that is the gradient of f. What's the magnitude of u? My unit vector. Unit vectors have a length of 1. So whenever you are finding the magnitude of a unit vector, that's just 1. And then you've got cosine of theta. Okay. If I want to make cosine as big as possible, what angle do I take cosine of? 0. So if the angle is 0, then the directional derivative is going to be the magnitude of the gradient times 1 times 1. And that's as large as it can be. If the angle between two vectors is 0, that means they point in the same direction, right? There is no difference in where u is pointing and where the gradient is pointing. So the direction that the function increases most rapidly is the direction of the gradient. So in fact, just to answer that here, it's the direction of the gradient. And that is always true. The direction of the gradient is always the direction of most rapid increase. And now let me ask you an easy question if you think about being on a hill. If I was on a hill and I said, that direction is the direction I'm going to go up the hill the steepest, what direction is the direction I'm going to go down the hill the steepest? The opposite direction. I'm going to turn around and be going down that way. So when you are asked about the direction of most rapid decrease, the answer is the negative of the gradient. It's the opposite direction of the gradient. And it's really, if you just think about literally being on a surface, oh yeah, I just turn around, I go the opposite way. So instead of going up, I'm going down. So to answer this question, the direction is going to be the gradient. But again, when we're talking about direction vectors, they have to be unit vectors. Why? Because your teacher doesn't want 1,000 different answers. Really, that's the real truth. The reason why we don't just say it's the direct, like this great vector, is because I don't want you to give me that vector, you give me that vector divided by 2, and you give me that vector. They all point in the same direction, but to be have a uniformity to our answers, we're saying, well, if you're talking about a direction vector, it has to have a length of 1 so that everybody gives me the same answer, and I can make it easier to write into web work. So our direction is going to be the gradient of f divided by the magnitude of the gradient of f. Okay, well, the gradient, we found it twice already. I feel like I don't need to do it again, but I should. So the gradient was, I believe, let's see, the partial with respect to f, partial of f with respect to x was 3x squared, and then we plugged in the value of 1. So that was going to be a value of 2. I said 1, sorry. And then the partial with respect to y was negative 6y, and we plugged in a value of 1 for y. And then we're going to divide by the magnitude of that vector, which is the square root of 3 times 4, so 12 squared, plus negative 6 times 1, so negative 6 squared. So this direction is going to be the vector, right? Because it's a direction, it's a vector. That's going to be 12 negative 6. And then each of those is going to be divided by the square root of 144 plus 36, which is 160. And yeah, I decided to write them in the vector this time. Although I normally would, I probably just still write this as 1 over the square root of 160 times 12 negative 6. So that vector is the direction where from the point 2, 1, the surface increases the most rapidly. How fast is it increasing? Well, we already did it. We said right here that if the angle is 0, which is going to give you the maximum derivative, then the derivative is equal to just the magnitude of the gradient. So the maximum increase, or I should say the maximum increase, or it's increasing most rapidly is how I should say it. It's increasing most rapidly. The value is just the square root of 160. That is the slope of the surface in the direction of maximal increase. So, to say it again, because it is definitely, I can even see it in your homework, right? Like question on the last part of your homework question, I don't know, 9 or 10. In what direction does this function increase most rapidly? In what direction does this function increase most rapidly? The answer to that question is always the direction of the gradient. So find your gradient at the point, then divide it by its own magnitude. Well, let's write it down one more time just so that we can see it again. So the direction that a function increases most rapidly in is the unit vector, the gradient of f divided by its own magnitude. As a quick aside, the direction a function decreases most rapidly in is the negative of that. Negative gradient of f divided by the magnitude of the gradient of f. And then finally, the maximum rate of change or rate of increase is just the gradient of f. The magnitude of the gradient of f, apologies. And those are things that come up over and over again. When you think about the gradient, you should be thinking about, if you're out hiking, I know I always come back to hiking because there are literal, right, topographical maps. If you're out hiking and you're looking at your map, you're like, I want to go in the direction of the gradient. Sorry, no, I took that away. Sorry, I'm trying to have all the things on the page at the same time.
Oh, okay.
Okay, cool. But okay, yeah, sorry. So if I want to go in the direction that's in the direction of the gradient, like from here, I'm going to be going that way. I'm going to be going towards the top as fast as possible. I'm crossing as many level curves as I can in the shortest distance possible. I'm going from a height of 200 feet to 300 feet to 400 feet as quickly as possible. Or in other words, my direction is perpendicular to the level curves. If you're crossing level curves in a perpendicular direction, you are going up the surface or down as fast as possible. Oh, there's something else I want to say there. Oh, no, I will. So just to kind of cap that off, the gradient is always perpendicular to any level curve. If you draw level curves, like if we go back to, sorry, I've got all sorts of things here. If we go back to that kind of one example I was drawing, can I find it? Maybe, yeah. Like if you go back to right here, to this example here, the gradient is literally pointing in the direction that is perpendicular to that level curve, which makes sense if you think back to the actual surface, because if I'm at that point, I'm asking what's the direction that's the direction of most rapid increase, it's literally the direction that is pointing towards the center of the thing, of the parabola. So if I move in that direction, I'm going to get shot up the surface because I can't just walk to the middle of the mountain, right? There's a whole earth in my way. I have to, if I try to go towards the middle of the mountain, I have to go up the mountain to be able to go in that direction. So the gradient points in the direction of steepest descent. All right, I think I said it enough times. I'll probably say it like 1,000 more times.